Hello. Okay, very good afternoon. Audible? I'm audible now? Okay. So just as a recap, we discussed Lipschitz continuity on closed and bounded functions, the relationship between these, and pretty much we showed that, well, smoothness, right, is a subset, kind of, there's a class of functions for which f is smooth. Is roughly kind of a subset of the class of functions for which it is continuous. And but then there are also further subset relationships between these two extreme ends, continuous functions and smooth functions. There is also this class of continuously differentiable functions, and there is this class of Lipschitz continuous function, which is functions which are differentiable almost everywhere. And we saw the relationship. We also saw that just like we have a relationship between strong convexity and convexity per se. Oh, for some reason, there's nothing coming up there. Don't know what I was supposed to do. Okay. There's this interesting relationship that a function f is Lipschitz smooth if for some non-negative constant L by 2 norm x square minus fx, basically. Instead of adding a strong convexity 1/2 norm x square, you are subtracting f from 1/2 norm x square, or 1 by L times the function from 1/2 norm x square. So this in some sense is also, we have a friend. This in some sense is also telling you that but the Lipschitz smoothness and convexity have kind of opposing effects. Strong convexity per more specifically. Okay, so we'll move on. We'll see more of Lipschitz smoothness and continuity coming up. Yeah, and we also saw the properties of F1 being Lipschitz smooth, F2 being Lipschitz smooth, then F1 plus F2 is also Lipschitz smooth. Well, what do you think about composition before we move on? What do you think of F1 composed with F2? What do you think will happen? Do you think F1 composed with F2 will also be Lipschitz smooth? So what do you know about the gradient of composition? We already seen, right? Subdifferential of composition is the sum of the individual partial derivatives of the inner component, of the outer component times the gradient of the inner component, right? Basically, chain rule. So based on that, based on the chain rule, can you say something about the Lipschitz smoothness of composition? What if I'll also tell you that you can assume some Lipschitz continuity property. What does Lipschitz continuity say? That the gradient is upper bounded, right? If it's differentiable of this L continuity, this is going to be very handy today. What did L smoothness say? Well, one base, if it's doubly derivative differentiable, then the Hessian minus Li is negative semi-definite. Negative semi-definite, right? So then what can you say about, so let's say I had L smoothness of F1, L smoothness of F2. Can I make any assertion about the composition? As I said, you can make any assumption you want about the the gradient being bounded. You'll trying writing down. So if I make some assumption, yeah, but anyone, first of all. So you can try doing both. One is the Lipschitz continuity and the Lipschitz smoothness. We already done the product. Product case, the function is bounded. So the gradient is bounded, sorry. Then the product is basically Lipschitz continuous. And the product is basically one instance of composition. Right? Basically, it's saying that if I have two arguments, or rather the same argument, but I just distribute that argument across the two functions with some kind of independence, then we have Lipschitz continuity of the product, assuming the function is bounded. That we have seen. Okay, so I'm going to leave you to think this, because this one property is important for some of these proofs, as we'll see. In fact, the first one itself. Okay, so logistic loss. This was a homework. Anyone thought about it? How would you prove a loss? I've given the proof sketch already. And what we'll do is just run over the proof sketch in the interest of time. So how do you solve this problem? You can consider minus yi theta transpose xi to be f2, right? That's a specific instance. Minus yi theta transpose xi, right? This whole thing is function of xi. I mean, there is a function of xi. And f1 can be viewed as log of 1 plus expt. So the claim is that this is Lipschitz smooth. And my claim is you can show that it is Lipschitz smooth by availing the property that compositions of Lipschitz smooth functions is Lipschitz smooth. Okay, so this is an obvious composition. Each of them is Lipschitz smooth or no? What about yi theta transpose xi? It is Lipschitz smooth. It has I mean constant, even a constant function is Lipschitz smooth. It has an upper bound on the double derivative. What about this green part? Log of 1 plus exp t is it Lipschitz smooth? And what if you take the double derivative? Okay. Right, so here f1 is log of 1 plus e raised to t. And if you look at f1 dash, it's e raised to t divided by 1 plus e raised to t. Take the double derivative, it is e raised to t divided by 1 plus e raised to t the whole square. Right, if you take the double derivative, it is this part is obviously simple. Double derivative is 0. Okay, so to compute its double derivative, we have used the quotient rule. The derivative of AT b divided by BT is A dash T BT minus A B dash T AT divided by BT whole square. The denominator whole square. That's how we get 1 plus e raised to t whole square in the denominator. Now, is this upper bounded? Yes. What is it? Asymptotically? As t goes to minus infinity, it goes to 0. Is it upper bounded? It goes to 0, fine. But we are interested in upper bound. Can I say this is less than or equal to half? Can we actually write it as a quadratic expression? E raised to t less than or equal to some quadratic expression. This should not be very difficult, right? Is this possible to write? So what is this? Sorry. Sorry. It will converge to some finite value. What do you mean converge to?
The denominator will be always
Hmm. Hmm.
Right.
Hmm. So close to 0. Yeah. So you're saying it will be upper bounded by something finite? 1/4. Sorry? So one of the things you should get into doing is just finding the highest value, right? Just take the right hand side. L plus L e raised to t minus e raised to t. That's fine. So this is greater than or equal to 0 is what we want to prove. But what we kind of want for some value of L. But you try and minimize it, right? That's one way to do it. But it's not difficult to prove that. This L is, if you set L to 1/4, what happens? Sorry? If you differentiate by, sorry? Differentiate what and put to 0? The e raised to t divided by 1 plus e raised to t whole square. And what will that give you? Yeah, so this, you're assuming that this expression here on the left hand side is a concave function, right? Or you're at least assuming that the critical point will correspond to a maximum. Taking the derivative and setting it to 0 means that it's a critical point, and if expecting that critical point corresponds to maximum means it should be concave in that region or concave globally if it has to be a global max or supremum, may not be min max, may not be attainable. Okay, so it's not very difficult to show, right? I will not spend more time on this. So this is L is 1/4, or you want to be more liberal, say L is half. It doesn't hurt at all. That's what I've written there. L is half or 1/4. Okay. The second one is easy. So now this F1, F2 theta, therefore would be Lipschitz smooth. In fact, it's also convex. We have proved that earlier, so we won't spend more time on that. Okay. What about the hinge loss? The hinge loss, is it Lipschitz continuous, smooth? Well, I've already put a claim there. It's Lipschitz continuous. Why is it Lipschitz continuous? So hinge loss, if you recall, I said that sometimes you'll have to prove things by considering cases. So what are the cases you can consider here? That the max is 0, which means 1 minus yi theta transpose xi is less than 0. That's one case, right? What happens then? The other cases, of course, when y minus 1 minus y theta transpose xi is actually greater than 0. In fact, I've taken a much simpler case, max of 0, 1 minus t. Okay, so I just replace this yi theta transpose xi by t. Made it simpler. So first of all, you think of cases. Then you think if each case can be made further simple. And here is our simplified case. 1 minus t. Then what have I done? Well, I have said, well, and so I'm getting very, very threadbare. You may not want to get so refined. But I've said, well, if case 1 is t is less than 1 or t is greater than or equal to 1, Sorry, T1. Okay, T1. So here you have T, but you're looking at two T's, right? So basically, since you're looking at Lipschitz a continuity, unlike smoothness, so I've considered here the case of ft1 minus ft2, right? And we'll consider the cases under which the difference can be upper bounded by some L, the absolute value of the difference. So I've considered cases where, okay, and then there's a particular form, or that this function has max of 0, 1 minus t. But now I have to consider a case where t1 is less than 1, t1 is less than 1, and t2. So the 1 is a threshold here. T2 is less than 1, or sorry, greater than or equal to 1. You can consider all, I mean, the numbering can be different, or T1 is greater than or equal to 1 and T2 is less than 1. Okay, let's just take one case here in the board and then the rest, it's all on the slides as well. Right? What happens here? In all these cases, is there an upper bound L? If T1 is less than 1, then what happens to the max function or f itself? 1 minus T1. Right? And T2 is greater than or equal to 1 becomes 0, right? So this difference is, let's call it difference, will be what? 1 minus T1, and T1 is less than 1. What do you know then about this L? Likewise, you can say if T2 is the same thing. Okay, so what about these two cases? Diff is 1 minus T1 and diff is 1 minus T2. Are they upper bounded? So case 1 is here, right? So this is 1 minus T1 minus 0, which is the same as 1 minus T1, which is less than or equal to T2 minus T1. See, remember, oh, sorry, I forgot the main thing. This should be less than. The right hand side was missing, right? So it is less than or equal to T2 minus T1. Right? Why? Because T2 is already, I mean, let's take the first case, it's T2 is greater than or equal to 1. And T1 is less than 1. So this is 1 minus T1 absolute value is less than or equal to T2 minus T1 absolute value. Is this clear? So in this case, you'll see that 1 minus T1 is less than or equal to T2 minus T1, which implies that L is anything greater than or equal to 1. Likewise, when the diff is 1 minus T2 is the same thing, 1 minus T2 absolute value, which is less than or equal to T1 minus T2, the same thing. Absolute T2 minus T1 and T1 minus T2 will mean the same. Again, you'll have L greater than or equal to 1. Is this clear? So, well, L equals 1 is also fine. L greater than or equal to 1. Likewise, all these three cases you can solve. Okay, so would you expect smoothness here? Lipschitz continuity is fine, but do you think smoothness is possible here? Well, we won't expect smoothness because you would see amounts to differentiability of its gradient almost everywhere. Right, so if you go back to this statement, differentiable almost everywhere. L is Lipschitz continuous, which is fine. But gradient f is differentiable almost everywhere is when f is smooth, right? Whereas this function gradient doesn't even exist everywhere. And we are talking about gradient being differentiable almost everywhere. You see, there's difference. The gradient was supposed to be differentiable almost everywhere for F to be smooth. So I think these kind of intuitions will be very helpful. So we won't expect smoothness for the hinge loss. Is this clear? Putting all they have learned to some use. Right, and then this is done, but after that we consider a composition of the function f above with a linear function. So what is a linear function? Yi theta transpose xi. So compositions in general preserve smoothness / continuity. Okay. How about multi-class logistic regression? Pretty much any property that holds for logistic regression holds for multi-class as well. Right. So this is generalization of the logistic loss case. Least squares. Okay, so this is strongly convex Lipschitz smooth. Why? Because it is quadratic. Moment something is quadratic, upper bound, lower bound, there's an upper bound growth rate and lower bound on the growth rate. Right? So this is about T square is both Lipschitz smooth and strongly convex. We expect least squares to be Lipschitz continuous in a bounded domain. Okay. The first three, of course, are also convex. Least squares is also convex. Now come to the interesting combination. Now all kinds of combinations you should consider. Okay, we are not looking at matrix completion, etc. Please do look at those as well. But let's look at the regularization version. So L2 regularization, the moment you put that, your strong convexity and Lipschitz smoothness. L2 regularization itself. But is it necessary that when you add L2 regularization to hinge loss, will you get Lipschitz smoothness? So my question is, this is fine. This is Lipschitz smooth and strongly convex. Now when I add L2 regularizer to hinge loss, which is just Lipschitz continuous, which we know by virtue of the fact that the gradient not being differentiable everywhere cannot be Lipschitz smooth, right? Hinge loss is not Lipschitz smooth. Now if to a non-Lipschitz smooth objective I add a Lipschitz smooth regularizer, do you expect Lipschitz smoothness? The answer is no, right? You can subtract a convex function from a quadratic L2 regularizer, say, and expect Lipschitz smoothness. So Lipschitz smoothness in the subtraction works, but not by addition, not by default. Right? You have to do more hard work, but in this case it won't. So you can't just add an L2 regularizer to hinge loss and say I've got Lipschitz smoothness. No, unlike strong convexity. Is that clear? Continuity, Lipschitz continuity generally is easier. You can expect Lipschitz continuity of L2 regularizer with hinge loss. That should not be a problem. Okay, so the same reasoning as least squares. The reasoning of L2 regularizer is exactly the same as least squares. L1 regularization is only Lipschitz continuous. So you can add L1 regularization to hinge loss and get, right? So to do this hinge loss, this was hinge loss, just add plus L1 regularization, you get Lipschitz continuous. Not a problem. Okay, so we showed that one norm of X is Lipschitz continuous. Okay, now so these are explicit combinations. L1 regularized logistic loss is Lipschitz continuous and convex. So logistic loss is Lipschitz smooth, but L1 is not Lipschitz smooth. So L1 plus logistic won't give you Lipschitz smoothness. It's only Lipschitz continuity. Is this clear? So I'll write this down so that it registers. Okay, so Lipschitz smoothness does not carry forward by addition by default. By default, you can't just carry forward. Lipschitz continuity generally carries. Okay, generally can. I mean, actually, it's addition since most functions will be. No, but still be careful. Lipschitz continuity also you have to do some hard work, like we did on the right hand side. Okay. So sum of Lipschitz continuous functions, Lipschitz continuous, sum of convex functions is convex. And L2 regularized logistic loss. So logistic loss is Lipschitz smooth. L2 is Lipschitz smooth. Therefore, their combination is also Lipschitz smooth. Right. So this smoothness carries forward as, when both components are addition. Have you seen this? Addition of Lipschitz smooth functions is Lipschitz smooth. Okay, so that's what we saw here. If a function f1 is Lipschitz smooth and f2 is Lipschitz smooth, the sum is also Lipschitz smooth. Right, and I've kind of also alluded to the fact that and so is okay. I think we are done with most of those cases. L1 regularized hinge loss. Again, Lipschitz continuity is what we'll get mostly. L1 is not smooth. Hinge is not smooth. And L2 regularized hinge loss. Well, it's Lipschitz. By the way, again, smoothness doesn't imply continuity. But on a bounded, right, a set where the function is bounded, then you can talk about Lipschitz continuity. So that's why I've added this specific case. Lipschitz continuous on a bounded set. Strong convexity is fine. One of the components is good enough to make it strongly convex. L2 regularized least squares, lasso is both Lipschitz smooth and strongly convex. Again, this is the best of the cases. Then, in some sense, this one, the L2 regularized logistic loss and L2 regularized least squares. So this is not lasso. This is called ridge. This is a typo. This is called ridge, not lasso. Lasso is actually L1 regularized least squares. Yeah, L1 regularized least squares is lasso. That Lipschitz continuous and strongly convex, but on a bounded set, because least squares is on Lipschitz continuous only on a bounded set again. Okay, I think we are done with a lot of the background for algorithms and their analysis. Any questions? So, why is all this useful? I'm going to give the intuition first and then plunge into some analysis. Until midsem, we should be completing most of the analysis, right, initial algorithms part, and motivation for accelerated methods. Now, what is happening is that if you look at the level curves here of the function, there are two key components of any algorithm: the magnitude of the descent and the direction. So, for example, if I'm in this level curve here, pink one, right, and if I go in a direction which is not normal to the level curve. Right? If I am, let me code as well. So as I descend from one level curve to the other, and this may be my direction. And as you can see, if I have taken a direction which is not normal, I'm not saying that it's a bad direction, but in many cases, this can mean that I need to take a longer step, right? Because the direction was not the best. On the other hand, if I take the right direction, I am possibly content with a shorter step. But just because I've taken the right direction doesn't mean that I can afford to be wavered in my step size. Because it might happen that these are my level curves. And therefore, if I overstep the yellow one, right? Even the right direction with the wrong size of the step could lead to overshooting. Okay. Is this clear? The simple illustration. I've tried to put the same thing on the board, on the slide. So magnitude direction. So what are the key points here? To analyze convergence, we would like to know how fast the function changes. So the fact that this function curved here, earlier I didn't show these curves, right? I just showed part of the function. But the fact that this function curved suddenly, which means there was there was a reasonably high upper bound on its curvature. That knowledge could have been helpful, right? In regulating the size of the step. Instead of curving this way, if the function had curved very leisurely, right? Then let me show the other one as well, outer one. So I'm just showing the same curve, same thing, but from a different perspective. Let's say until here, they seem to have similar behavior, but thereafter it just turns very gradually. Here I can actually afford to have same thing, much bigger step, because I know that the function is curving very gradually, which means it has a very it doesn't have a tight upper bound on its curvature. Oh, sorry, it has a yeah, it has a tight upper bound on its curvature. I mean, the curvature is not high, right? So that's the reason Lipschitz smoothness helps, because Lipschitz smoothness basically says the Hessian is an indication of the curvature. It says basically the eigenvalues of the function are less than or equal to some lambda or Li. Eigenvalues are bounded upwards. And you know, eigenvalues are kind of the length of the axis. So if you have an ellipsoid, you remember the major and minor axis are the lengths of the eigenvalues. So think of that. Think of that as an example. That's why Lipschitz smoothness helps. But Lipschitz by strong convexity also helps. If you know that the function is actually very strongly curved, then you can also be a little careful. In fact, what you could do is use kind of momentum from the previous steps to accelerate, right? In case you know some properties of the function such as strong convexity. But we'll see a little bit more of that later on. More that will come up, right? So curvature is important. How fast the function changes, what's the curvature of the function, Okay, I mean, how fast the function changes is also important. So this was only curvature, but how fast the function changes. Basically, I don't have more colors here. More colored pens aren't around. But imagine I had so imagine I had information on the rate of change of the function itself, not just the curvature of a particular level curve. Then I could possibly also estimate that the step size, for example, if the function is changing very rapidly, decreasing and then increasing again, right? Then I could use that estimate to be careful or conservative about my step size. So rate of change of the function, curvature of the function oscillating. I mean, these are again related, right? And additionally, convexity. So we have not even talked about convexity so far. But if I knew that the function is convex, then the fact that there's the function change seems to be showing a local minimum here would also hint that this minimum is a global minimum. Okay. So yeah, so the goal is given a convex function. If we'll do analysis for convexity, but as I said, the algorithms have all been used for non-convex functions inspired by convex regions of non-convex functions. So the goal is to make sure that you get an iterate f of x star, which is close enough to f of x. Now, for the rest of couple of classes, two things will come up. One is x star and f of x star. Okay, and I have a question to you. What are you interested in? Are you interested in x star or f of x star? What is your interest? So what is x star? Let's see. Argument of f of x and f of x star. So there are two things you could look at, right? One is the distance from of x from x star. The other thing you could look at is the absolute value of fx of the difference of f of x and f of x star. Which of these two would you be interested in? Also, a related question is find an x. Sorry, x star. Find an x star. Yeah. So I'll put that star. Yeah. So you want to find an x star, but are you trying to characterize the distance of x from x star or the distance of fx from fx star? Fx from fx star. Why? Right. See, it's possible that your x is very close to x star, but still the divergence is very high. Okay, so now you'll find that sometimes the proof leads you only to difference of x from x star, which is not good enough, right? But that is unfortunately how life is. Right? A quant company overtakes, right, shakes up the world with DeepSeek. Right? That's how life is. So you don't know. I mean, you think that I'll land up with some characterization in terms of f, but you get x star. Unless you put in some fancy properties like Lipschitz smoothness. So let's also keep our kitty. What all we have in our kitty? We have in our kitty. Okay, we'll use there only, right? right here. Properties to use. What are the properties we'll use here? What do you think are the properties we'll pick from our Gini? One is convexity. I'll begin the list. Convexity could sometimes also be strong or strict. What else? Lipschitz continuity. The third, obviously, is Lipschitz smoothness. Now, are there more we can add to this list? Properties to use. We'll not just say properties, we'll say tricks. So there are some properties and there are some tricks. Okay. Well, some more properties will also come up. We have not exhausted the list. I'll add one more property to the list. Okay. So I want to get close enough to X star. Now, does it hurt saying that my initial iterate, like let's say I have an iterative algorithm, my initial iterate is not too far from X star, or rather, the further away my initial iterate is from X star, the more time I will take. Is that reasonable to assume, right? So can I say that the distance of X naught from X star is less than or equal to some R? My first iterate is within some R radius, within some R radius ball of X star. Is this reasonable to assume? So that's also a property we may use. And there'll be some tricks that we will also use. So goal is given a convex function, find an X star. And first of all, we expect X star to exist if it's convex. Okay, so that's important. If it's convex, and we have seen under certain reasonable properties, right? Weierstrass function was an exception, right? But typically would expect an X star to exist such that X star corresponds to the argument and my function estimate is less than within epsilon radius of the optimal. So the iterative algorithm we'll begin with is the simple gradient descent. So that's also a property in some sense. We didn't list it, but it's also a property to use. The property is that my iterate xt plus 1 is some gamma times the gradient direction, negative of the gradient direction. Okay, so there's a gradient descent algorithm. So we'll also denote it by GT. GT is basically gamma times negative of the gamma times negative of the gradient of f, negative of gamma times the gradient of fxt. So you can think of xt plus 1 is xt plus gt. I don't know if I use gt as negative or whatever, right? But let's just for the time being write as negative. So the gamma is, as I said, is important. This is the gamma. This is my xt. This is my xt plus 1. And this direction is the negative of the gradient in the case of gradient descent. But we'll see a little generalization later on. We'll start with the simplest. which is very popular, but very soon we will look at okay. Okay, so this gamma is a magnitude part, and general descent algorithms, what they do is they replace this gradient, negative gradient, with GT. That's what I've done there. I've used GT there more generally, right? But specifically for our purposes, this GT is nothing but minus of gradient times fxt. And we have seen enough of gradient, right? It points orthogonal to the level curve at that iterator point. Okay. Yeah, and as I said, it can be dangerous to set a large value of gamma here. Now, an important point, while I said curvature, etc. are important, the rate of change of the function in setting up the magnitude of the gradient of the step, the direction itself is also important in determining the magnitude. Right here you see, I didn't take gradient, I took some other direction, and therefore I need to be a little more careful about the magnitude. Magnitude should depend on the direction. So there are conditions such as R mu. We have not listed them here, but as we progress, we'll also put some conditions on the magnitude. Okay, so this is upcoming. I'm not going to write it here. Later, there is R mu conditions on gamma. And these RVO conditions on the gamma are themselves in terms of the direction. Okay, so you need to sensitize. I think with this, we come to the main question for the remainder of today's and next few classes. How much time? All this is great, but what does it result in terms of the time required to get to within an epsilon proximity of f of x? Right. So what we want is, so let's say I just now start putting xt here, f of xt minus f of x star, and I want this to be f of xt minus f of x star to be less than or equal to epsilon. Right. So the question I'm asking is to get to this. What is t? What is the order of t? Okay, can you guys guess? Like how should t be? What would you be happy? What value of t? What order of t would you be happy with for epsilon? I give an epsilon. I say, well, give me a nice value of t. Yeah. Sorry? Huh? I couldn't understand. 1,000. Oh, you're giving a fixed value. Okay, 1,000. Okay. A fixed value of t. What else? Huh? Huh. So you're saying the t can be a function of gamma. But number of steps is what I want. I want to know how many steps. How many steps does it take so that f of xt minus f of x star is within epsilon? So I understand that, t would be a function of gamma. What else? Okay, t could be a function of x naught. It's not visible here. Yeah. I'm still seeking some relationship with epsilon. How do you think T should vary with epsilon? It's basically a trade-off, right? If I want to get very close to f of x star, then I might end up taking a lot of time. But what is that lot? Is it inversely varying with epsilon? The smaller the epsilon is, the larger the T, obviously. Huh? There's some anti-monotonicity. But how anti-monotone? Is it reciprocal? What are the other functions you can think of? You get my question? T is function of x naught is fine. Should be of the order of 1 upon epsilon. Is that a good behavior? Depends on the function. That's true. That's what I've written. Function could be convex, Lipschitz continuous, Lipschitz smooth. We don't know. But what is the ideal? So, what would you like the convergence to be, irrespective? And then we'll work backwards the nature of the function, right? Or the algorithm, or the gammas. What would you desire? 1 upon epsilon, are you happy with it? Okay. So you're saying T should be order of log of what? Minus log of epsilon. That's the same as saying log of 1 upon epsilon. So he is saying not just 1 upon epsilon, log of 1 upon epsilon. Right? 1 upon epsilon is still slow. Log of 1 upon epsilon will be much faster, and we'll see that. Right? You could also say, okay, both are two extremes, but I could say, well, log of order of 1 upon e raised to k. If k is greater than 1. 1 upon epsilon square, 1 upon epsilon is to 4. Right? Okay, so this is the question. How much time? 1 upon epsilon square, log of 1 upon epsilon. And you can see of the 3, the most preferred will be 3, right? Log of 1 upon epsilon. That's more preferred than 1 upon epsilon square and this one. I'm sorry. 1 log of 1 upon epsilon is more preferred than 1 upon epsilon, which is more preferred than 1 upon epsilon square. Obviously, 1 upon epsilon is better than 1 upon epsilon square. Epsilon is small. 1 upon epsilon square is going to slow things down. Okay. So let's define x star as a global minimizer of f, and let's proceed. So we're going to start with f being Lipschitz continuous with parameter b. We'll start with this Lipschitz continuity. And if f is smooth, then you may also consider parameter L for Lipschitz smoothness. Okay. So Lipschitz continuity is what we'll begin with, because as I said, that's more generic. You already saw the relationship, right? Lipschitz continuity amounts to a function being differentiable almost everywhere. Lipschitz smoothness amounts to function being, the gradient of the function being differentiable almost everywhere. So smoothness is rarer commodity. So to begin with, at least for the rest of today's class, we'll drop Lipschitz smoothness and see. Right? So we'll just drop Lipschitz smoothness. But we'll see that this leads to weaker guarantees. Okay, so that's no surprises. Lipschitz smoothness gives you better convergence. Okay, so yeah, I mean, what is the notion of fast versus slow, right? You look at these iterators x1, x2, x3. So here you see the step has led to big jump from x1 to x2. But then as you go towards x5, sorry, yeah, things can get slowed down, right? This of course also is assuming that the gammas are not fixed. The gammas can be adapted, the step sizes. Now, for most purposes, we'll consider adaptive step sizes. So first analysis. Okay, now a little bit of analysis. I hope we can finish this in today's class. And what we will do is, instead of writing down everything in the on the board, I'll write down the key steps. So we have already written some key things we are going to leverage. I'm going to remove Lipschitz smoothness for today. As I said, that's not going to be assumed. Rest of the properties we'll need today. I think a strong convexity also we will not use. Okay, so this is the first analysis we are doing. I'll add to that list on the right hand side, I'll add some more tricks. On the left hand side are just properties. On the right hand side, we'll add some tricks. So I won't write down detailed steps. Okay. So first is the gradient descent step. I have used GT as gradient. Okay. So there's a slight notational difference. The slides I have used GT as just the gradient. So I'll remove gamma from GT. Okay. Just to be consistent with the slides. And GT is, so the descent, the GT is not the step. GT is a gradient. So XT minus gamma GT is the new iterate XT plus 1. We just make the adjustment for of this notation just for the analysis here. Okay, so GT, so the key thing is GT transpose XT minus X star, just by definition, is 1 upon gamma XT minus X T plus 1 transpose X T minus X star. So what have I done? All I've done is, so this is a trick. First trick I've done is dot product. And I'll tell you why dot product. So dot product has been kind of in our DNA so far. We always looked at whether we are tangential or normal to the hyperplane, right? So in some sense, we're looking at the dot product, make zero dot product. We also looked at dot product in the directional derivative case. So think of this as some kind of directional derivative, right? The dot product is directional derivative. So what is it basically showing? What is this directional derivative? I mean, modulo constants is proportional to which directional derivative? Current xt. Okay, so what is this? Dot product for unscaled directional derivative. I'll write this also on this slide because I've not written it there, but that's the intuition here. Yes, so what is this directional derivative with respect to? Anyone? Yes, anyone? Can we give some name to it? There's a current iterate xt, and then there's an x star which I aspire to get to. So what is this showing? The directional derivative along the direction from current iterate to the sought after point, right? Unscaled directional derivative along the direction from current trade optimal solution. So it's a trick we are obtaining because I'll call it a trick because this nice you apply tricks on useful entities. It's a very useful entity. Okay, so this is a for unscaled directional derivative along the direction of the current okay. Now what will I do with this? Can you think of we'll do step one step at a time, right? Before I do that, let's also give some names to it. So I'm going to just simplify this. These are two components here. I'll give them the names U and V. Okay. So xt minus xt plus 1. So this xt minus xt plus 1 is gt, right? Transpose xt minus x star. So this thing is gt, and which gives you the directional derivative. And we'll all just call it u. We'll call the second component v. Okay, u transpose v. So the second trick we're going to adopt is as follows. U transpose v, any dot product U transpose v can also be written as what? Can I expand it in some quadratic terms? And why am I interested in quadratic terms? Look at many things here. X naught minus x star. Think of it as square here, right? Lipschitz continuity is in terms of norm, which involves some quadratic term, ideally. You'll find that quadratic terms become very helpful. So in the moment, as a dot product, it's a well motivated dot product. But I want to expand this as some quadratic term. Can I write this in some form? Can I write this as u square, blah, 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 blah. Is this okay? 2 u transpose v is u square plus v square minus u minus v whole square. Is this correct? Should I use this or some other expression? Of course, what I've done there is not just u square, but yeah, norm u square. I'm sorry, this is norm. Okay, I use VW instead of UV. That's okay. So the W doesn't matter. So this is the first trick. This is the second trick. Expanding or simplifying the dot product into quadratic terms. I call it simplifying because those quadratic terms can have inequalities associated. Whereas the dot product, you can't do much by itself. So this is a trick we often invoke. Transformation of dot product to quadratic expansion. Is that okay? I think pretty much we have everything on the board as well here. So now, yeah, that's all. So 2 u v transpose w is norm of v square plus norm of w square minus norm of v minus w. Okay, so I just used different notation here, u and v. If you want to just change it to u and v and w. So let's just keep it consistent. Let's just call it v. No. Okay. So this is done. So we have rewritten the right hand side now, right? By just expanding. The dot product is now written as three quadratic terms. So the next trick, now we come to the next trick. So we have two tricks employed. What would be the next trick? The next trick too is to realize that there's something interesting going on here. What is interesting going on here? So I have actually, I have not expanded on the board, but the slide, what have I done? I've expanded. GT transpose XT minus X star is 1 by 2 gamma, XT minus XT plus 1 norm square, plus XT minus X star norm square, plus minus XT plus 1 minus X star norm square. So how did I get this? Well, what did I do here? The negative part, XT plus 1, like this part, V minus W was XT minus XT plus 1 minus XT plus. So I basically, this XT gets cancelled out. I'll have XT plus 1 minus X star remaining. Right? So this part simplifies. So XT plus 1 minus X star. So why is this interesting? Well, it is interesting because this give you V minus W norm square, give you XT plus 1 minus X star. On the other hand, W was norm of XT minus X star square. So if you consider us summing across different values of T, right? For T equals 2, you'll have X2 minus X star norm square minus X3 minus X star norm square. Whereas for 1, you'll have X1 minus X star norm square minus X2 minus X star norm square. So the X2 minus X1 norm square, you understand? For T equals 2 gets cancelled with the X2 minus X star norm square for T equals 1. That's called telescopic summing. If you do a telescopic summing, if I sum across different values of T, I'll have many of these terms cancelling out, right? That's another place where your mouth should start watering. Oh, some terms can get cancelled out. So I'm going to erase the left-hand side of that board. The next trick we are employing. It's called telescopic summing. So that X2 minus X star norm square minus X3 minus X star norm square plus X1 minus X star norm square minus X2 minus X star norm square plus blah blah blah. Of this, you can have for T equals 2, one term getting cancelled, T equals 1. Likewise, T equals 3, the X3 minus X star will get cancelled out. T equals 4, X4 minus X star will get cancelled out. Right? So instead of wasting no space on the board, we'll jump to the expression on the slides. This is what we have done. We have summed the left-hand side from T equals 1 to T minus 1, capital T minus 1 of the dot products. On the right-hand side, something interesting happens. Very interesting things start happening now. And it is not just by coincidence. Certain things get cancelled out, but certain things start getting accumulated, which are also reminiscent of some of the other properties. So so far have you used convexity? No. So far have you used Lipschitz continuity? No. X naught minus X star? No. Right? Only this property, XT plus 1 is XT minus gamma GT. That's the only property we have used. So 1, 2, 3, well, 1, 2, renumber it. 1, 2, and 3 are yet to be used. and they will start surfacing. Okay. So you start getting something called gamma by 2 norm GT square. What does that remind you of? Norm GT square should remind you of Lipschitz continuity. And then, of course, you'll have an expression involving GT xt minus x star, GT transpose xt minus x star, and x1 minus x star. So some of the other terms. Okay, they'll come up later on. But the fact that you have GT transpose xt minus x star still there on the left hand side should make a case for convexity, right? What is the first order definition of convexity? Yes, f of xt plus 1 is greater than or equal to f of xt plus gt transpose xt plus 1 or whatever, right? I mean, minus xt. In fact, it will not be in terms of f of xt. In fact, I will use x star here. Let me actually expand. The convexity property we want to use is f of x star is greater than or equal to f of xt minus gt transpose x star minus xt. Okay, this convexity property will become very handy here. Okay, so yeah, this is just to tell you what is there to come. Okay, so we have summed over the t iterations. The expression, right, which are on the previous slide, I have summed over t iterations. I have this dot product summed over t iterations, GT transpose xt minus x star. On the right hand side, by telescopic summing, a lot of these have got cancelled, right? What has got cancelled? Xt minus x star has got cancelled with xt minus x star from a previous iteration. Xt plus 1 minus x star is getting cancelled with xt plus 1 minus x star in the next iteration. The part in yellow are getting cancelled. So then the next questions are asked. So with that simplification, I'm asking the next question. Can the green term be upper bounded based on convexity? Because that we would like to exploit. Can the orange term be upper bounded based on Lipschitz continuity? Okay. So we are done with, I think we have no more tricks currently. We are probably now at the cusp of just finishing off the solution. Okay, so I'll write down the final expressions now. We are pretty much there. So I'm going to invoke convexity on the left hand side. Can this term be upper bounded based on convexity? Right. So what does that mean? Xt minus x star, swap it, bring GT transpose xt minus x star to the other side. Xt minus x star, yeah. Or yeah. So I'll write that. So GT transpose xt minus x star is less than or equal to f of x star minus f of xt, right? What the term there involves is summation. T equals 1 to t equals 0, sorry, to t minus 1. The summation here. Likewise, the orange part. So I unfortunately don't have different colors, but this is a green part. I'll just use the green outline. Likewise, there's an orange part there, which is gamma by 2 summation t equals 0 to t minus 1 norm of gt square. Can I upper bound this based on Lipschitz continuity? Yes. What is this upper bounded by? Gamma by 2 times L times B, right? No, not L times T times B. B is a Lipschitz continuity constant. T is the number of iterations, the number of summations. Okay, so this is the part in orange. I'm just using an outline of similar color. That's it. These are the two pending things. Is there something I can do with x naught minus x star as well? What do I know about x naught minus x star? The initial iterate. It is not too far away. I mean, the further away the initial iterate is from my optimal point, the more time it will take. And that's obvious, right? So this x naught minus x star, you see on the slide, can also be upper bounded. And that is here. X naught minus, in fact, I don't have to write it again. X naught minus x star is less than equal to R. Just be very careful with inequalities, right? Just because you've got 3 inequalities doesn't mean you've solved the problem. I mean, the inequalities may be very inconsistent with, right? Mutually inconsistent. Here they don't. Here you're able to, basically able to show that this term is upper bounded. Right, this, and then you can and then that is further upper bounded and so on, right? So not a problem. Things just, so I'll just use the slides to continue this discussion. Okay, so first thing I said, as I said, is the part in green there on the board. I'm invoking convexity. F of xt minus f of x star is less than equal to the dot product of gradient with xt minus x star, and that can be rearranged, right? All I've done is rearrange. I've got the gt transpose xt minus x star on the other side, right? And that's what I've written on the board. GT transpose xt minus x star is less than equal to f of x star minus f of xt. It is flip the signs. And then I have used this fact that xt minus x star. Oh, I have also used one more fact which I forgot to mention. Is xt minus x star also sitting around, right? That was also unnecessary. Xt minus x star is always greater than equal to 0. And because you have negative of xt minus x star, things just work out because negative of xt minus x star is less than equal to 0. Okay, so that is an additional small thing. Negative of xt minus x star is less than equal. Actually, if you look at it, everything is upper bounded. Everything is being upper bounded. Negative of xt minus x star is being upper bounded. X naught minus x star is being upper bounded. The sum of the gradient squares is being upper bounded. This dot product is being upper bounded. Everything is being upper bounded. Right? So just complete the analysis on all the elements we have already brought together. That's all. We just have to now put together the 4 components, 4 inequalities we have, all upper bounds. Is this clear? So parts in green, the GT that I have written on the board, and the part in red, xt minus x star is already done. Right? So we are basically now getting summation of f of xt minus f of x star is less than equal to gamma by 2 gt square, which will upper bound by b times t, and 1.2 gamma x naught minus x star, which will upper bound by r upon 2 gamma r. Okay. Okay, that's it. The part in red, this part, or the part which you had written in orange, is Lipschitz continuity, gives an upper bound on the gradient norm square. This part, xt minus x star, that we have got by upper bounding gt dot product with xt minus x star. And yeah, I think this, so remember, this is the first order convexity condition. Okay, now we have come to a very interesting point, the final result. There's one small step, right? We are saying that sum of f of xt minus f of x star is less than or equal to gamma by 2 norm gt square. Okay, so this gamma by 2 sum of norm gt square is nothing but t times b square. Oh, by the way, it's b square. I made a mistake here on the board. It's b square because norm gt is upper bounded by b. Norm gt square is upper bounded by b square. Small mistake on the board here. So you see there's a tb square gamma by 2 exactly there. Then the from the I know that 1 upon 2 gamma x naught minus x star is less than equal to r square by 2 gamma. This is r, right? X naught by x star is less than equal to r. So I got r square by 2 gamma. One small thing, right? What about this expression? See, this expression still has a summation f of x star minus f of xt. What do I do with that summation? That one small step is remaining. I have iterates, right? So visualize this as follows. I'll just conclude. I have iterates. I have x1, x2, xt, and they're getting close enough to x star. They're supposed to be, which they're supposed to get close enough in f. So what can I assume about f of x star minus f of xt? Can I assume that this entire expression is less than equal to the summation something? Okay. So you'll see on the next slide, right? So we have many elements put together except for that one term, but that one term is also going to be resolved. Okay, so first of all, this is E1. E1 is summation over R, so T, f of xt minus f of x star. This is independent of gamma. E2 is this expression, gamma by 2 times TB square plus R square by 2 gamma. The upper bound we got for Lipschitz continuity plus the x naught being within radius R. That is E2. Now there are two more tricks remaining. Okay, so one trick. One trick is that this expression has gamma. And somehow we don't want gamma in our final. I mean, we want to say, well, even if you use the best value of gamma, the most informed value of gamma, you'll take so much time. So the trick here I've done is, if this is an upper bound, like this is an upper bound, I said everything is upper bounding. That's how things are working out. I'm saying this upper bound is less than equal to some value. And that less than equal to value will be by minimizing with respect to gamma. See, it's basically saying that E2 gamma will be less than equal to min of E2 gamma. I'm sorry, the E1 is, what I meant is E1 is less than equal to E2 gamma, then E1 will be less than equal to min of E2 gamma. Because E1 did not have gamma. Okay, I'll just write down this last trick and then we are done for today. So the last trick, I think this is there are two more tricks, but the fourth one is really not a trick. Let's conclude this. I don't want to make this pending for next time. So this is the fourth trick. We have E1 which is independent of gamma, less than equal to an expression E2 which is dependent on gamma. What is the expression E2 dependent on gamma? Gamma by 2 TB square plus R square by 2 gamma. And E1 is this expression, the sum of all the function differences, the iterate differences from x star. This part is independent of gamma. This part depends on gamma. So all I'm saying is, if E1 is less than or equal to E2, which is a function of gamma, then it must be the case that E1 must be less than or equal to min over gamma of E2 gamma. You understand? This is a trick, very important trick. Minimize the upper bound. When the LHS doesn't have the variable, minimize the upper bound with respect to the variable that the left hand side doesn't have. Okay. So the trick is minimize RHS upper bound with respect to variable gamma that LHS does not have. You get this trick number 5? Oh, sorry, trick number 4. This is a fourth trick. That's what we are showing on the slide. So on the slide, I'm writing the expressions. On the board, I'm trying to write the intuition. Hope that's okay. Right? I don't want to write the math again. So this is the trick number 4. Now, when is this? When is gamma by 2 TB square plus R square by 2 gamma minimized? When is it minimized? You can take the derivative with respect to gamma, set it to 0, right? And it's minimized when gamma is R by B square root T. Okay, so this basically R by B square root T. If you set gamma to that, then you will minimize the right hand side. And if you substitute R by B square root T, you'll basically find a square root T come up here. It becomes square root T R BR, I think will come plus will you get something like this? Is that the expression you get here? I think it will come in the next slide. Okay. Oh, actually, yeah, something. So I think I put an extra B here somewhere, but you should just get it to be RB by square root T. RB, I think there will be some 2 here. Yeah. RB square root T divided by 2 plus RB square root T divided by 2 will give you RB square root T. Oh, by square root T, I see. I think yeah, RB by square root T, something of this form. Okay, so the minimum will be RB by square root T. The left hand side, actually it will be square root T. I think I have divided the left hand side. This is 1 upon T. That's correct. It was RB square root T. That's correct. So when I divide the whole thing by 1 upon T, I'll get a 1 upon square root T on the right hand side as well. Anyways, the last trick, oh God, it's already 10 minutes. But the last trick is this f of xt minus f of x star. Instead of saying every value, instead of summing over all values, I can just take the least of those values, right? Just like I minimize the right hand side. If I take x hat as argmin over I of fxi as a final iterate, then I can show that t times that min value of f of x hat minus f of x star will continue satisfying this inequality. Okay, so this is just going to be something you need to look at, right? We just take x hat to be the argmin of all of those guys, show that f of x hat minus f of x star satisfies the same bound, but multiplied by a factor t. Okay, so I think this is just, I'm going to leave this as homework for you guys. I think we are over short time. So the final bound you'll get, and this is where I would like you to think a bit more. The final bound you'll get, I'll leave this, is the time required. Okay, this is the key. The time required is at least r square b square by epsilon square. Remember I talked about 1 upon epsilon square, log of 1 upon epsilon and all that, right? This is 1 upon epsilon square. Given a Lipschitz continuous function f, gradient descent with step size gamma is r by b square root t achieves. I mean, this is the worst case. Right? This is basically min value. But in general, any gamma should achieve a solution x hat in r square b square by epsilon square iterations. Not a good situation to be in. You should not be happy with it. It's really bad. 1 upon epsilon square is bad. Right? It's worse than 1 upon epsilon. It's very slow. Okay, so I think we'll continue this next time. The homework problem for you is to think, how can we make it faster? The reason we went through this proof, we'll not do this for every case. Okay, we went through it in great details. The key is to understand where can we make it faster? Where could that 1 upon epsilon square have become 1 upon epsilon? When can that 1 upon epsilon become log of 1 upon epsilon? And that's a homework problem. Is it okay? So I'll leave you with the homework problem. How can this entire proof, where in this proof methodology can I get log of 1 upon epsilon? Can strong convexity give me that? Can Lipschitz smoothness give me that? Right? Many other elements will remain the same. Telescopic summing, you'll find everywhere. Right? The minimization, this E1 less than equal to min of gamma E2, you'll find coming up everywhere. So this, please pay attention to the proof methodology and look for places where you can speed up. Thank you. Thank you. Or show better speed up. The same algorithm that shows that it has better speed up. Thanks. Yeah. The other homework problem for you is to think, how is it related to the order complexity we hear in algorithms, right? O, big O, big O, omega. How is it this? How is this related to big O and omega? So I have actually, I have rate an order of convergence, my notes I put on Moodle. Have a look at them and understand how is it related. I mean, is it big O? Is it omega? What else Theta, theta. Is it related to any of those? Yeah, we'll stop. Sorry for really going overboard today. I didn't realize time. Thanks.